Hi, everybody. My name is Matt. I'm going to talk to you about microservices, as it seems everyone else is. So hopefully this won't overlap too much with the other talks. And basically about Go and how we're doing this at Monzo. So little quick intro, as I said. So my name is Matt. You can find me here on Twitter, so if any questions, I'll be around all day. But otherwise there, you can also stalk me around the internet, which will be very uninteresting. And I work mainly as a back-end engineer. So I kind of work on distributed systems. I've been doing Go for about 3 years now, kind of almost full-time. And I used to run the platform team at Hailo, which was an on-demand taxi app where we had like a globally distributed Go microservice platform. However, today I'm talking about Monzo. So Monzo is a startup I work for. We're based in London. And of all the things we thought we'd do, we would like to replace banks. And banks are an interesting area. They've kind of been around forever. This is how banks kind of appear to me. I go into branches. I have like weird people staring at me, and I have to like queue up at counters and do things. And certainly in the UK, banks are not very good at kind of adapting to the modern world. The way you access these things online is terrible. And fundamentally, that's because at their core, they're built still on mainframes, which run COBOL. And like, if you wrote COBOL in the 60s, well, if you wrote code in the 60s or 70s, you can still run that on like Z-series mainframes. And these things are critical. They process like billions of dollars of payments a day. So like getting changes into those, modernizing them is crazy. And as an example, Barclays in the UK spent £3 billion a year on IT. Hands up anyone who's spent £3 billion this year on IT. One or two, okay. So like, if you're a startup and someone gave you £3 billion, like imagine what you could do with that. And really, like, this is the modern world. Everyone's on their smartphones. So at Monzo, we're trying to change that. We're mobile first, kind of smartphone app. You can do basic things like actually have contextual information rather than just a dodgy statement. So you can work out where you've been. You can search with emojis, crucially, very important functionality. And you can do things like, I don't know, like if you've been out for something where you need to record expenses, you can record receipts. And you can take pictures, attach them to your transactions. I actually use it to attach pictures of my brunch, because I like to remember what I've eaten. And other kind of really basic things like being able to turn your card on and off. Magic. In the UK, that takes 7 days. You get a new one sent to you through the post. Whereas this is a bool flag, right? It's a flag in the database that says whether the card works or not. You check it when it goes in the machine. It's really not very hard. Like, seriously. Maybe it's an enum. Like, you maybe want like temporarily blocked and permanently blocked. So we now have 4 states. Magic. Anyway, so if we're going to start from scratch, and if you could build core banking infrastructure right from the ground up, where would you start? Usually, you'd start with kind of a basic application and a database. And to be fair, for startups, this is what you should be doing. The main challenges that startups have are really kind of like market fit, making sure you're building the right thing for customers, and being able to like iterate really, really rapidly. But we obviously hear lots of stories about how this kind of pans out over time. So your application gets bigger. You add more databases potentially, maybe some searching things, caching, all these extra things, and like millions of other things that you need to like scale up your application. And fundamentally, you get to this point where you have one gigantic thing that everyone is working on. And it's usually like, I've seen, my experiences, there's kind of 2 aspects to this. There's obviously like technical scaling, but there's also like scaling your team. And this is a recurring theme with companies that migrated from these monolithic applications to microservice platforms. Because this is kind of what it is. Like, if you've worked in a company which has a massive application and everyone wants to get changes in, and then you have to deploy the whole thing in one go, this is my expression when I want to make some changes. And there's obviously lots of better ways. We could take our application, we can start breaking it apart, and we end up with potentially lots of small discrete services. Which communicate between themselves. And those might be synchronous, they might be RESTful, you might use RPC between them, or you might use like event-driven architectures. in which case these things will be subscribed on some form of message bus. So why did we choose to start with microservices at Monzo? So for us, we're integrating with the banking networks. And I say on the end of that because we're integrating with a lot of different networks. All sorts of things like anti-money laundering, like actual banking networks for every company, card processors, those kind of things. So we had to abstract these things away. If anyone's interacted with those systems, like we're talking, I mean, SOAP would be great. Like that is the level that we're on here. And I'll be honest, like the SOAP support in Go is not amazing at the moment. It's got a couple more improvements coming along. Oh. Not sure what happened there. Yeah, the SOAP support's not great, but I mean, that's infinitely better than like binary formats, which you have to deal with. Like the ATM network, that's all like characters smushed together, and there's like these 5 characters of this thing, and then the next 6 of this thing, and you have to pull them all apart. So for us, we needed to abstract these things away. And that meant that we actually had discrete pieces of software for these things. And my experience at my previous place where we moved and migrated to a microservice platform was we wanted that speed. We wanted to be able to move quickly and iterate different discrete sections of our application. And there are a few kind of things that we're aiming at here. So single responsibility principle. Every single piece of our infrastructure, we needed to do one thing and do one thing extremely well. And that meant that we could focus on how it worked internally, we could scale it better, teams could coordinate a lot better just on that thing. Make them simpler so you could understand exactly what was going on. And an easy way to do that is to bound the context of these things. So in the real world, that means if you have a problem space, you can subdivide it into lots of discrete sections. So banking, for example, you tend to have bank accounts, you have cards. And these are easy things that you can chop apart and they do one thing. And on top of that, you then end up with really nice interfaces. So these are the interfaces not just between your like technical components, but also between the teams who are building these things. And a lot of companies have talked about this. Having well-defined interfaces means that you have very well-established patterns of communication. But the nice thing on top of that is once you have all these things built out, you get like really awesome composability. So if one area of your company has had to build like some extremely resilient like push notification system, probably not that hard to write. Once you have that, you can build lots of features on top of this. You don't have to rebuild this functionality every time. And that means actually once you've kind of done this migration step, you have lots of abstracted components that you can build new products on top really, really quickly. So why would you migrate to a microservice architecture rather than starting? And the real reason for this, and this is something that we've come up against at Monzo, is unless you really, really understand your problem space, you can't make those decisions. You don't know where the contexts begin and end. You can't divide these things up. And that means that your interfaces then aren't defined correctly. And then you have to like iterate those. And that's like really painful. Changing all these things, deploying lots of different things like different versions, and having to deal with all of that just because you didn't understand exactly how this abstraction worked to start with is a bit of a problem. So if we were going to start, we'd probably have some load balancer at the top with DNS, etc. And behind that, we'll have like some HTTP API or some API of some form. And in our case, we have this more as a routing layer. So we can take this, and then we can take all of our requests, do like kind of SSL and TLS and everything at the top, do various other rate limiting things, and then push these into some form of transport. That might be HTTP between services, or it might be a message bus, something like that. You might use like AMQP. And then behind our services, which are doing these discrete jobs, they'd all have their own databases. And this is a very important kind of concept that these things shouldn't be like accessing databases of other services. One, because it's just really hard to manage. Like, if you have your really nicely defined interface at the top, and then you have like abstractions that you've had to build up over time, where your data models may be changed, if some other service is like directly reading the database, that's like hell. So once we have this kind of thing, we can like parcel this up, run it in multiple data centers, And that's it. So Go. Hands up, anyone here who's used Go or uses Go on a day-to-day basis? Okay, a few people, cool. So Go is obviously a fairly new language, and that comes with pros and cons. For me, Go is extremely simple. The language itself is really, really small, so it's really easy to learn. It's easy to pick up. And you can be productive on like a day-to-day basis within like a month or two. Beyond that, obviously, it's statically typed. So if you're writing financial applications, it's quite nice for you to like not randomly flip between integers and floating point numbers. That's quite important for bank balances. And then static linking means that you can compile single binaries, and you can put those anywhere. So you can compile them for literally Unix architecture, Linux architecture, say AMD 64, and you can just pop that on any machine. You don't need like a runtime installed. You don't need any dependencies. And that's awesome. So any of the ops people out there, like, this is really cool. You can like put them in like deb packages and just install it, and there's no runtime dependencies. It's literally like a 10 meg file. It's amazing. And then on top of that, Go has really cool language features. So concurrency is built in from the start. You can literally have a function call, and you can put Go space before it, and it will run concurrently. Now, there's a pros and cons to that, obviously. You now have like a million things running in order, and you have no idea what's going on. But it means it's really easy to build network services. And the interface support means that you can actually you can have a transport, for example, which we'll come on to later, and you can have a mock transport that has exactly the same interface, and you can just swap it out. You can swap it out literally while you're doing your tests. So your tests might use like an in-memory mock rather than having to have like loads of infrastructure running. And on top of that, the standard library in Go is amazing. So although the language is very small and very compact, the standard library has stuff for everything. So networking is a good example. If you want a HTTP server, that's about 4 lines of code. If you want a HTTP 2 server, you take those 4 lines of code, you wait for Go 1.6 to come out early next year, you recompile it with no code changes whatsoever, and you have a HTTP 2 server. It's magic. And like, that's in the tip version of Go now, and it will be released early next year. But Go just has these things built in. But if you wanted to actually start with like a microservice architecture, we need some components to build on. Although it's really easy to build like a HTTP server, like, it would be nice if there were like higher level constructs to build these things, so we don't have to write loads and loads of boilerplate. So in Go, there's a couple. There's one called GoKit, which allows you to build really nice services, and it has client libraries that interact with that. And it allows you to build like all of these extra things that you would expect from a microservice architecture, or any service-oriented architecture. Things like circuit breaking, you can build in tracing, that kind of stuff. Micro is also really cool. And there's a couple of other gRPC, which I think has come out of Google and Stripe. That's like a cross-language kind of thing, so you can compile bindings for Go, and Kite as well. And in Monzo, these things didn't really exist when we started writing them. So we have our own versions. So we have Typhon, which is our transport layer, and Mercury, which builds on top of this to provide a client and server implementation. So these are MIT licensed. They're on GitHub at those addresses. And the aim of pushing all of this functionality into our libraries is to allow us to, with a few lines of code, spin up a server and then talk to it from a client and deal with all of like timeouts and kind of connecting to the right things and service discovery, and we just abstract all of that away so that I can write services really, really quickly. And that's really the thing that we're aiming for. We're aiming for like incredible velocity. That's like the main selling point of us moving to this kind of architecture. So to go back to our example, we'd have our load balancer, our API, and then underneath that we have like a tier of services. So we call these like API services, and what these do is they provide like marshalling. So if, for example, we had a webhook path on our API, which we do, that allows you to register webhooks, delete webhooks, those kind of things, so that every time you use your card in a machine, you can have registered applications which get an immediate notification. But all that means is we have our API as a routing layer, which takes anything /webhooks lar and passes that through into this webhook API, which is a discrete service. And once it's in this webhook API, we can do anything we want. In our case, we're going to pass this on to a couple of other things. There's probably some other things I've omitted here. So we'll do things like authorization and then actually put the webhook into the database and have a service that then knows and listens for transactions happening, where to send these webhooks. And these will have their own databases. And to be honest, this applies to any API in our infrastructure. So you might have all sorts of other things happening, going off to external providers. If you're taking cards, you might be tokenizing them, like so be going off to some third-party processor, getting a token back, storing the token in your database, that kind of stuff. But at this point, we're really all talking like kind of synchronous calls. So we have some call that's come in, it's gone to a number of services, we've done some database writes, gone back out. And we kind of joke that most of what we do is marshalling JSON in and out of Cassandra. So we use Cassandra for most of our databases. And that's really all we're doing. Like, we get the request in, put some data somewhere, request out. However, we want our architecture to be as resilient as possible. So actually, a lot of our like asynchronous stuff is event-driven. And we do the smallest number of synchronous calls possible. So in the case of a card, we might check that you have enough money and then like log the transaction and then return back to the card machine. But then there's like a huge amount of other things we want to do off the back of that. So when our request comes through, we can then publish these events. We publish them onto like an internal fire hose. And we use NSQ. You could use Kafka, anything like that. And all this is doing is publishing like a well-known, I think JSON description in our case, but a well-known like event that describes what's happened. And then any number of things can subscribe to that. So if we have a number of services, these could subscribe, and then they may, off the back of that, do multiple other synchronous calls, emit additional events, that kind of thing. So we'll end up with some other things happening, and that probably gets quite complicated, and we have no idea what's going on anymore. So when I show a service like this, what do I really mean? And in Go, as I said, these are discrete binaries. They're a single program, single process that runs on a machine. We run lots of copies of each one. But inside these, we obviously have like a lot of things going on. So in our case, we break this up into kind of three main areas. Right at the top, we have a number of handlers. So these are the methods, the endpoints that are called when we get a request in. Obviously, they'll have some logic associated with them. And underneath that, I've put storage here, but I mean like other things. So like databases, putting things on queues, calling external providers, that kind of stuff. And in our case, we're using our Mercury library to provide this kind of service abstraction. But all that's doing is letting you register multiple functions which are called. And these have an interface like this. So this is a Go interface. There's a type. It's called handler. And it's a function that takes a request and returns a response and an error. And this is a very common pattern in Go. A lot of function calls will return things, and it's got multiple return values, and then an error as the last parameter, which may be nil if there was no error, or an error that matches a particular error interface. And the really cool thing about Go interfaces is that anything that matches this, that has this function signature, can be used as a handler. So you could have a struct that has all sorts of data inside it, all sorts of other methods, but as long as it has a method that takes a request and returns a response and an error, then you can use that as a handler. So we register a number of these, and then we have a transport, which we push things in and out of. So again, this is really simple. We can have any form of transport. It could be HTTP, it could be AMQP, some kind of asynchronous message bus. And it has lots of things, which we don't really care about, because the important ones are that we need to be able to listen for new things coming in. We need to stop listening if you want to shut that down. And for every message we maybe want to respond, and if we want to send new requests to other services. So again, in Go, we can use the interfaces here to literally put anything, as long as it matches this interface, as a transport that we can send messages to and from. And in our case, we use AMQP internally, so we have a really nice transport for that. But when we do tests, we don't want to run like RabbitMQ and other things. So we can have an in-memory mock, which satisfies this and pretends that it's moving things between services. And actually, all of our event-driven stuff goes through this as well. So the only difference is that we're sending a request and not expecting a response. And the cool thing there is that if we're using the same interface, we can register the same middleware with everything that we're doing. So we can get all sorts of things for free. And then on top of this, we'll have various storage things. So we push as many things into libraries as we can. And these kind of give you like a lot of stuff. And the really cool thing here is like the aim of templating services is that we want me, if I want to add some more functionality, I don't want to deal with any of this stuff. Like I don't want to deal with monitoring. That should just be magic, right? I should be able to fire up a new service, and as long as I've like followed our path, I write some functions that provide some functionality. They do anything I want. I then compile it, ship it. It goes through our build process. We deploy it, and the fact that these are like known functions means that I should get timing data off that. I should be able to record the number of errors and record the errors, but I shouldn't have to deal with that if I'm just writing the logic in the middle. So being able to like push all of these things into like your templating system is really cool, because you can like knock services out in like 20 minutes. Like I want a new section of API. All I have to do is clone a template, write some code, which is literally a function, and then I can ship that onto our infrastructure, and that new subsection of our API now doesn't 404. Now we actually have some functionality there. And things like service discovery are like quite complicated, but if you can push those things down and deal with the fact that once a binary is running, it needs to be like heart beating to other things, these things are kind of solve problems largely. Service discovery, you can use things like console. If you build your own, you can build it on top of ECD or Zookeeper. Configuration, either you'd be using like either command line flags or config files, or in our case, we have a separate config service which we make requests to and from. And the nice thing there is that we can register callbacks, so that when our Cassandra IPs change, like I don't want to know about that. I've written some software that like just wants to have some Cassandra and write data into that and read it. And I'm going to assume that when our Cassandra servers go up and down, that our configuration service will change, the IPs will change in that, and then my service will automatically update. So once we have our block, our discrete binary that we can ship, obviously we need some way to deploy this. And a nice easy way to do that is with Docker. Maybe, yeah. So for us, if you're writing stuff in Go, you actually get a lot of the advantages without containerization. So if you, I used to work on PHP applications, in which case you had like a huge number of dependencies. You had to manage all of those, and getting the right dependencies with like the right PHP extensions on every machine was like an absolute nightmare. So putting those in containers is awesome, because you have a discrete unit you can ship, and it works in every environment. But actually with Go, you already have a discrete unit. There's no runtime dependency. So the main things you're gaining by containerization are the tooling that you can use around Docker, the whole Docker ecosystem, and also like the basic things like C groups. But you could do that yourself. So in our case, we package these up into Docker containers. And the cool thing is, because there's no runtime dependency, you can make the containers really small. So you can use Scratch images. Has anyone used Scratch images here? Like one person, okay. So if you're using like an Ubuntu image, that's like huge. So you've got what, like a 500 meg container, and then you have a 10 meg binary inside it, and it has no dependencies on any of the stuff inside this container, but you just have to ship this massive image around. Whereas in Go, you don't need that. You can literally compile your binary. You can put that inside a Scratch container. Magic. However, although I said Go was statically linked, that's not always quite true. And you have to provide specific build flags to make sure that it does actually link link statically, rather than using stuff like the native DNS resolver. Otherwise, obviously, you can't make requests to anything. And on top of that, a Scratch container doesn't have any of your root certificates. So a common problem is that you would put your thing in a container, you ship that, and now you can't do TLS, which is a bad thing. So you can literally copy your certificates into your container, and then you're good. And the end result is you have like a 10 meg container, maybe 15, and you can push that into any number of different services. So Google Cloud, you've got Google Container Engine, ECS, the container service on Amazon, or Mesos or Kubernetes. And in our case, we use Mesos, so we use Marathon Scheduler, and that means that we can tell it to run n number of containers. We can give it constraints like anti-affinity, so it won't run more than one of the same containers on the same host. And other things like, please distribute these evenly across multiple racks, multiple data centers, and run like a number of them in each one of these areas. And if they restart, if they die, then restart them, that kind of thing. So the main problem we have having done this is that we've got a huge number of extremely simple components. And Adrian talked about how things are complicated, and sometimes they need to be. I'd say in our case, some of these things are. Other things probably would have been easier if we just built it as one application. But the benefits you get over time will vastly outweigh that. And the way that we can kind of deal with this mainly is by testing. So we can fire huge quantities of traffic at our microservice architecture, but we're doing specific types of testing, right? We need to do load testing, obviously. It'd be nice to know at what point we'll fail over so that we can do like capacity planning and really know how well our individual components perform. And then we can decide which areas to optimize. However, specifically in our case, we need extremely high uptime. Everyone needs high uptime, right? So we need to be doing failure testing, and we want to be doing this continuously. So if we have our tests running, we want to be terminating services, nodes, databases, those kinds of things, and asserting that our like system still works. And also we're doing degradation testing. Now for me, this is the really important one. So I don't know if anyone's had, I'm going to pick Memcache as an example, something where your service is just really slow, but is not dead. In which case, what tends to happen is, if it's dead, you go all the way through, you try and read or write to your other system, it dies immediately, and then you get a response. And the response is an error, but that's fine. Whereas if, say, that takes like 200 milliseconds longer than usual, then these things kind of tend to back up. And then you have potentially like retries, and you get this cascading failure all the way through your system. And this has happened to me before. Memcache took 100 milliseconds longer than we were expecting. We didn't have a timeout. And the end result was that we took everything down. Everything crashed. And as long as we're putting timeouts in there so that we fail fast, then we can kind of get around these things. But we need to be testing that those things do actually happen. And you can do this on Linux quite easily. You can use IP tables to like simulate delay. Or a good one that we had on Amazon was where the connection was in an established state and it accepted the packets, but the packets didn't make it through the interface. They just got dropped. So like our timeouts were like, it's cool, it's connected within the timeout, it's all good, and then nothing, which again took us down completely. So the next step beyond that is then monitoring. And monitoring is an interesting one. There's a huge range of different type of monitoring you can do. In our case, we do the standard kind of like monitoring individual nodes, but monitoring your services is where you can like do really cool stuff. So we provide internally another kind of like Go interface. So any function that returns an error and optionally a map of like additional information. And what we do is every service can, the interface allows you to just register multiple ones of these. And then our library will take care of like actually passing these back to the monitoring service and heartbeating so we can determine whether the machine is still up and the service is still up, but that these health checks are now failing. And these could be anything. These could be connecting to your database. They could be counting the number of outbound TCP connections if you're like making lots of outbound things. So you can work out if you're like slowly filling up like beyond the number that you'd really want to be running. But for us, crucially, the thing we want to do is monitor our business logic. So who has acceptance tests? please, everyone put your hands up. OK, there's lots. Good. What I found really is Go has really good testing infrastructure built in. So you can really, really quickly write tests and run them. It's super fast, and you can mock things with interfaces, so it's great. But if you have an extremely simple application, it's easy to write lots of easy unit tests that always pass. And then you have to put a bit more effort into write ones that actually provide real value. And equally, if the internals of your service are changing all the time, then those unit tests are of more limited value, especially if you have a request that passes through lots of different systems. It's really those kind of integrations, the interfaces that you want to test. So if you have acceptance tests that run through all of your infrastructure and exercise all the real code paths that your customers use, then those are a much better way of testing your system. And for us, fundamentally, customers are the only important thing. It doesn't matter if our services are screaming and all these things are down. If you can still get money out of a cash machine, and if the app still works, but it's in a degraded state, then that's a lot better than if everything's broken. So we have obviously you have standard out-of-band kind of things. You can ping the API. You can make sure that these machines have enough free memory, that kind of thing. But then beyond that, actually having in-band stuff that's going through the same transport as your customers are using, and running your acceptance test in production, but with fake accounts, if you can do that, that's a much, much better way of testing, because you can assert that the customers are not seeing broken behavior, or that they're seeing a specific degraded experience. And in our case, we do this. We simulate money transfers, which are real transfers. They go through the same production infrastructure. And we just bounce these between specific accounts. And those tests are running from infrastructure that's outside of our data center. So we run it through our normal API, so it's exactly the same experience. And beyond that, if you have a complicated infrastructure, then tracing is probably the best way to understand how these things interact. So there's a lot of different approaches here. Zipkin is a great tool that you can use to fire off information all the way through your thing. And what I mean by that is, if we have 3 different services, we have a request-response kind of thing all the way through, then right at the top, we can generate some unique ID for every request, something big like a type 4 random UID. And then we can pass that through our request. So we can pass that along and pass that through to the next service. And then we can understand, we can add instrumentation data with this request ID, so we can understand how that one request flowed all the way through our different components. And in Go, you want to propagate this context. So there's a really cool context library, which again has a particular interface. So actually what you can do is you can build, there's various things here, but the one we're interested in is this value thing. And that is a key value store. It's immutable though, so it's completely thread safe. You get a new context each time. But the cool thing is, all you have to do is satisfy this interface. So actually our request type has this method on, and therefore it satisfies the context interface, and we can pass it through any tooling, and there's various libraries that allow you to use this specific interface. And then you can do things like put a trace ID in right at the beginning, pass it all the way down the chain, and then pull it out at the end. So if we have our interface, our request like this, we can send specific sections, like instrument-specific things, like timing data, which host every one of these services is running on. And we can fire all of these things off, either into something like Zipkin, or at Monzo we have a tool called Phosphor, which is similar. And what that's doing is taking all of the various bits, aggregating all of those things together, and spitting out a massive blob of text like this, which is clearly very useful. But the cool thing is you can then actually understand what's going on, because you can generate tracing things. So this is actually a real one from our interface. So this is, I put my card in a machine, typed in my PIN or used Paywave, and we have a request into our API. And that goes into a specific card API, goes into a card processing thing. We then do various things like checking that you have enough money, that the card is actually real, that's the thing. And the end result is that we do all this synchronously, and then we fire an asynchronous event to say that a transaction was created with all the various information. And a lot of things can then subscribe to that and do really cool stuff. So we then have a thing that goes off and takes the very small amount of data that we get and tries to use like Foursquare and Google Places to like identify which actual shop this is, which is something you don't get on a normal bank statement. And we can do that, and then once we've done that, we might publish another event to say that this has been enriched. And then the end result of that is we have something that actually puts it into the feed in the app, and then fires a push notification, which again is asynchronous. And all of these things, we have like really nice breakpoints. So if something crazy is going on, our whole push notification thing is down, then those things will just queue, and as soon as it comes back up, we'll send them all through. But those things won't affect our card processing. And I mean, the timeout that we have here is about 100 milliseconds. That's the contract we have with our card processor. So we need to do as small a number of things as possible within that synchronous time frame, and then everything else later. But the cool thing is this might take ages, but it doesn't. I get like a push notification like this, which crucially has a coffee cup, because we know it's a coffee shop, and I get that before the receipt prints in the machine. It's like 200 milliseconds. So like, again, this is not hard stuff. It's like really easy technology, but like is not something I can get with any existing bank. So these things are quite easy to build. And then this is actually a gross simplification of what we do, which is more like that. Lots of other things happen. And the cool thing is as well, like we have like all the edges between the services, right? So we can measure these. We can measure timing data. We know whether they succeeded or failed. We know the percentage of those, the upper 95th, 99th, and the upper measurements. So we can do cool things like build like visualizations that map all of our services communicating to each other. So why would you choose Go if you were building services? So for me, it's small, it's like simple, and the language itself is really, really easy to learn. It's got amazing concurrency. So for network services, it's perfect. You can like spin off tons and like tens or hundreds of thousands of Go routines and run them concurrently. And the memory usage is quite low. The garbage collector is really good. And all of that just kind of is really easy to work with. Interfaces are amazing because you can like mock stuff and swap out transports. It makes your code really, really easy. And the networking support's really cool. So downsides, not a huge number of people in here have used Go. So that's one downside, obviously. It's a new thing to learn. And for all its pros, like the standard library is great, you always need third-party libraries to do things. And being a younger language, those are varying quality. There used to be problems with dependency management. That's kind of now solved, but that involves usually copying the entire dependency tree into your repository and locking it at that version. So if you were starting with microservices, or migrating away from a monolithic application, I'd give Go a shot. It's really easy to use, and you can plug it in just with a HTTP server. And that's about it. Thank you very much.